So hello and welcome everyone. My name is Jay Dalsaniya and in this video we are going to solve the question maximum connected group. Okay, so this question is quite interesting and it has got many concepts that we can utilize in order to solve this question. And if you are really enjoying the problem of the day, then do hit the like button and share your approaches in the comment section below, and we would like to know your thoughts as well. Okay, so without any delay, let's start the video. So the name says maximum connected group. Okay, so let's first of all read out the problem statement. It says you are given n cross n grid. A grid is considered binary if every value in the grid is either 1 or 0. You can change at most one cell in the grid from 0 to 1, and it says you need to find the largest group of connected ones. Two cells are said to be connected if both are adjacent to each other and both have same values. Okay, so basically it is saying that you will be given a grid of 0 comma 1, a binary grid, and you are supposed to find out the maximum connected component. But there is a catch that you can basically let's say if there is a cell with the 0, you can convert it into 1, but you can apply this operation only once. That means on a particular cell only. Basically, you can select any one cell and you can convert its value from 0 to 1. And after converting that cell from 0 to 1, you have to find out what is the size of the maximum connected component over here. So, didn't get the question? Don't worry, I'll take an example to get you an idea. So, let's see an example to understand this thing. Okay, so now let's take a binary grid. Okay, so I will be taking a binary grid, and here it says the size of the grid is going to be n cross n. Let's take n cross n equals to, in our case, let's say 3 cross 3. So I'll take a binary grid, a random grid, okay, 1 0 1 1, and let's take 1 over here. Okay, so this is n cross n grid, 3 cross 3 grid, and contains 0 and 1s. Okay, so now find out the connected component. Okay, so connected component says that if a cell is present over here, if then the cell above it is a adjacent cell. The cell on the right hand side, downwards, and left hand side are called the adjacent cells. Okay, so now if we find out the connected component containing all ones, right, that is what the question is saying. Find out the connected component containing all ones. So here is the connected component, and what is the size? Just count the number of cells: 1 2 3, 3 plus 3 6, and 7. It says the size of this component is what I came out to be 7. Now the question is saying that there is one cell, that is one operation that you can do. Take any cell with 0 and convert this into 1. Now let's say if I convert this into 1, you know that now this can be like this is adjacent to this component, right? So now this entire thing becomes one component, and if I basically change this 0 to 1, the size of this component will become 8. Okay, so by changing this cell, I am getting a size of connected component of 1 that is equivalent to 8. Now let's take one another one. So let's say if I change this 0 to 1, you can observe that this is the entire component that I will be getting if I change this, and then also it is contributing the size of 8, right? Because it is only helping us to increment the size of the component by 1. So here by changing one of the cell from 0 to 1, you get the maximum size of the component to be what? Output comes out to be 8. Okay, so this is what the question is saying. Let's take few more example because I can see that this question might be difficult for some beginners to understand, and the difficulty level of this question is hard, right? So now let's take one more example. What I will be doing, let's say 1 1 1, and let's take 1 over here. I'll take 0 over here. I'll take a 1 1 1 and 1, and now let's take one more 0 and let's take 1 over here. Okay, so now let's convert, let's take all this as zeros. Okay, so now this is a better example. With the help of this, you will be getting an idea. Here, n equals to 4. 4 cross 4 grid is given to us. Now, first of all, what you can do is find out the connected components. Okay, so here is the connected component, and its size is equivalent to what? 4. Here is the connected component. Its size is also equivalent to what? 4. Here is the connected component. Its size is equivalent to what? 4. Okay, now let's see what we can do. If I change this 0 to 1, let's say if I change this 0 to 1, we know that now this cell will be adjacent to both this one and this one, right? So now what will be the entire component? This is going to be the entire component. Okay, and if I see what will be the size, it will be 4 plus the cell which we have converted plus 4. This comes out to be 4 plus 4, 8 plus 1, 9. So one answer that we got is 9. Let's say maximum answer, or let's take the answer that we got till now is what, 9, by doing the operation on this particular cell. Now let's choose another one. Now let's say instead of this, what I'll be doing, I'll be choosing another one. So here, if I choose this cell and if I convert it into 1, it is going to give you the connection between this component and this component, right? So the overall size of this will be equivalent to 9. See, similarly, if I do this, then both this will be connected and I'll be getting answer 9. So all these cells that are present over here, if I try out on every 0, we know that it will be joining this component and this component, right? So here it is giving this answer. Similarly over here, if I change this cell basically to 1, so it will be basically connecting this and this component. So overall, any of the 0 you convert, you will be getting the maximum answer to be 9 in this scenario. So the answer for this test case comes out to be 9. So now I hope you are getting an idea about this connected component thing, and the adjacent nodes are in this direction, in this way. If I say I comma j, then above up, then we have right, downwards and leftwards. These are the adjacents. Okay, in the question this is not defined, but this is what they are trying to say. The adjacent means up, down, left and right. Those are the adjacents. So I hope you got an idea, and just the key points of the question. So you are supposed to, basically one operation is possible over here. And what is that operation? One operation is take a cell having value 0 and convert it into 1. Okay, and you are supposed to find out the maximum connected component having ones, its size you have to find out. This is what the question is saying. Now I hope the question is clear, and these are the key points on which we are supposed to work. Okay, so now here comes the approach, like how we can think about this question. So if we have a look, so while I was solving this test case, you might have observed, first of all, I was focusing on finding out the connected components that are having all these cells as ones, right? So this is what we did, right? We basically found, where we were focusing on finding out all the cells, or let's say the connected components having value 1, right? That was what we were doing. So we can approach in that manner, right? We can find out all the connected components having cells 1s, but the question is, how will we keep the track of all those connected components, right? So basically the thing is, if I say this is a connected component, I got to know, let's say this is my component number 1, and for this component I will be storing, let's say, the size. What is the size of the component? I can know that is equivalent to 4. Then I will be having component number 2. Okay, so this is the component number 2 and its size is also equivalent to 4. Then I have component number 3 and its size is also equivalent to what? 4. So this is the component number 3, right? So we need some kind of way of storing a component and its size, right? Then what we are supposed to do, we are basically selecting a cell 0 and we are trying to convert it into 1. Then we are supposed to see how many cells for this 0 are adjacent. Okay, so let's say if I take this cell and if I convert this into 1, now I'm, let's say, converting this into 1. Let me just erase this, and okay, I've converted this into 1. Now you are supposed to find out the adjacent components. So here I can see the adjacent cell is this one, but this is already 0. So this will not contribute to the connected component. Now I can see this is a cell 1. So this cell is a part of what? It is the part of component number 2. Okay, so what you will be getting, you got to know that on the right hand side there is a component and its size is equivalent to 4. Okay, then you will be finding the connected adjacent cell in the downwards direction. So this is the adjacent cell. Okay, and it is 0, so it will not contribute to the size. Now here this is 1, right? So this one is a part of component number 1. This is component number 1, component number 2 and component number 3. Okay, so I have to find out that this cell is part of which component. So I got to know it is part of component 1. So here I can observe that the cell is inside component 1. But what about the code? In the code, how will you identify? So this cell is part of a component and its size is equivalent to what? 4. Okay, and now as I'm converting this cell from 0 to 1, it will also contribute its value. So it will be 4 plus 1 plus 1. So I got to know it is 9. So in this manner, what you can do, first of all, find out all the connected components having value 1. Okay, and then store it inside some data structure along with their size. Okay, that's what we did. Then what we need to do, then find out all the cells that are having value 0, and for all those cells find out the adjacents. Okay, find out all the adjacents. Let's say this cell is 0, then find out all the adjacents. You will find out over here, up, right, downwards and leftwards. Okay, and let's say all of them are 1, right? So what you need to do, you need to find out that this cell is part of which component, this cell is part of which component, this cell is part of which component, this cell is part of which component. And you also need to get the size of that component. So this data structure or something that you will be using to store the size will give you the size, and keep a temporary variable that you have to find out that if I convert a particular cell from 0 to 1, how much, like, basically it will impact on the answer. Okay, so here I got to know if I convert this cell from 0 to 1, it will give me a connected component of size 9. So keep a maximum variable, and let's say maximum variable says minus infinite. So you can update this maximum variable, and you can say basically over here, let's call this as what, 9. Then you can do the same process for other cells as well. Let's try to do for one more cell, so you guys can understand in a better manner. So I'll keep this connected component as it is over here, and this cell 0 was present, right? Now let's say if I choose a different cell, I'm choosing, let's say, this cell. Okay, and now I'm converting this into 1. Okay, so I'll be finding out what are the adjacent components. So I'll have a look at this cell, the cell above it. So the cell above it is 0, right? So it will not be the part of any component. The cell over here, this is 1, so it will be part of some component. So you have to find out this one is part of which component. I can say it is part of component number 3. What is the size of this component? It is what, 4. So the temporary answer, I will be storing 4. Then I will be having a look at the downwards direction. I can say this is 0, it will not contribute, it will be not part of any component, right? Then I will be seeing on the left hand side, I got to know this is 1, and find out which component this cell belongs to. This cell belongs to component number 2. And what is the size of the component 2? It is what, 4. So now this cell which we have converted will also contribute. So add its value as well. So what did you get? You get 9. So for this cell, you get the maximum connected component size is equivalent to 9. So compare with answer. Here we got to know that the answer is same, right? So we don't need to update the answer. So in this manner, you basically can find out, first of all the connected components having cells 1s, and then find out all the cells 0, try changing them to 1 and see the impact on the answer. That's basically what we are supposed to do. Okay, so now what we need to do, basically, like, how will we implement this thing? I hope the idea is clear. I'll just note down the algorithm if you guys have understood. So let's say, first of all, find out all the components having values 1, and store their size as well. Okay, so this is what we need to do. Then find out, basically find out means traverse the entire matrix and just locate the cells, right? The second thing is find out all cells with value 0. Now convert this cell to 1 and find out adjacent component and calculate temporary answer. Calculate size of component formed by this cell. And I'll be storing this inside what, a temp variable, and then you can keep an answer variable and keep on maximizing this answer. So you can just say maximum answer and temp. Okay, so this is the algorithm stack. First of all, find out all the components having values 1s. How many components are possible? Let's say n components are possible, 5 components are possible, and store this size somewhere. Okay, and it should be quickly accessible, obviously, for better optimization and for better time complexity. Then find out all the cells, then pick a cell, then now convert this cell to 1 and find out the adjacent component and calculate the size of the component that is formed by this cell. Okay, if you change the 0 to 1, then find out all the adjacent components, okay, and see what size they contribute. Okay, then store it inside a temporary variable. Okay, fine. So now I would like to explain with one more example over here. So let's say this is 1 1 1 1, let's check 1 1 1, and let's take 0 and 0. Okay, so I'm applying the algorithm that we have seen right now. First of all, find out all the components. So let's say I have some kind of structure in which I'll be storing the component and its size as well. So let's say I got to know this is one of the component that I can observe over here. Okay, so I got to know, I'll call it as component number 1, and its size is what? Its size is equivalent to 7. Okay, so I found all the connected components. It's possible that there might be one more component possible, right? So you're supposed to find out all the components, then one by one select a cell having value 0. Now let's select this. Okay, Now I'm converting this into 1. Now let's find out what size of the connected component this will contribute. Okay, now I've converted this into 1. So find out the adjacent. In above, nothing is there. On the right hand side, there's a cell having value 1. So this is a part of some component and its size is equivalent to 7. So I'll calculate a temporary answer that will be saying 7. Okay, now see in the downwards direction it is 0, so it will not be helpful. Now in the leftwards direction it is 1. Okay, so now you can see this is a cell having value 1 and it is part of the component, this component, and its size is 7. But you can see that this right hand side cell and left hand side cell are already in the same component, right? So this will not contribute an extra 7 over here. It will be basically, it is already calculated when you inserted 7, when you added the 7 inside this temporary variable. Okay, so you need to make sure that the adjacents are of which component. Are they of like same component that we have selected earlier, or they belong to a different component, right? So for that, basically you need to use disjoint set union. So disjoint set union, if you don't know what is that algorithm and what is that data structure, then I would highly recommend. It's a very useful data structure in graph when you want to solve questions with better optimization, and the questions that are related to connected components that can be solved using this disjoint set, as well as if you want to detect cycle in a graph, you can use disjoint set as well. Okay, so learn about disjoint set. So we can use a disjoint set to identify this component and its size. So this is the data structure that I was talking about, is nothing but your disjoint set union. Okay, I will be using disjoint set union to in order to implement this structure to store the component and its size. Okay, now if you already are aware about DSU, then you might have understood. Okay, so we can think about using disjoint set. We'll be able to find out that a particular node is part of which root, right? So in that manner we need to do. If you are not aware about disjoint set, pause this video, have an idea about what is DSU, then come back to this video and this question you will be able to solve it. So in this manner I can basically implement this thing. First of all, find out all the components, and for this I will be using disjoint set union. Okay, and then for this thing it's basic finding adjacent of a node and then just checking the size of the disjoint set that is adjacent. Okay, so I hope you understood the idea, what is the algorithm and how we are going to implement this thing. So now let's have a look at the coding implementation for the same, and let's try to solve this question. Okay, so the implementation part, basically the implementation part for this question is quite lengthy, so I would help you to go through the code structure. I also added the comments over here, so you will be getting an idea what we are doing, right? So first of all, let's have a look. This is the max connection, right? So this is the maximum connection and this function in which we are supposed to write down our logic. So I would like to comment, I would like to minimize this thing first of all, and I would like to first of all go with the disjoint set. Okay, so algorithm number, in the algorithm, step 1 is to find out all the components having value 1 and store their size. Okay, so I have created a disjoint set in which, if you are aware, a disjoint set uses a parent array and then it uses a size array. So this is a class which I have created and this is the initialization I have done. See, in disjoint set, every cell is considered as a node. Okay, in disjoint set, every cell is considered as a node, or let's take in this matrix, every cell is considered as a node. So how many nodes are there? So there are n cross n cells, so obviously n cross n nodes will be there, right? So I have basically initialized the parent with how much size? N cross n size. Let's say over here, when you basically create an object of disjoint set, n equals to n cross n. Okay, there are total n cross n nodes in the matrix. So parent will be of n size, and the size array which I have created stores the size of the component. Okay, then I have basically initialized the parent array, parent of I equals to I, basic initialization, and size of I is equivalent to I, because every cell is currently a part of its component and its size will be equivalent to 1. And here basically I've used find and union method, and basically the find method is I have basically written the find method using path compression, and the union basically that I have used is similar to union by rank. If you don't know what is union by rank, it's an optimization to union. Okay, so union, let's say two components are there, u and v. I find the parent of u and v, then I see if they are of the same component, then I just go, I don't do updation. Now let's say if they are not of the same component, then I basically join based on the size of the component. Let's say if this, see there are two components, u and v. Okay, u and v are the nodes. U is part of one component and its parent is pu. V is part of one component and its parent is pv. Okay, now I can see the size of pu or this component is less than compared to this component. So what we will be doing, the smaller one, what I will be doing, I have done parent of pu. I am saying that pu, the another component, now you are part of the larger component. So I'm updating the size of this component, the larger one, and I am basically changing the parent of the smaller component. Okay, so what I was saying right now, let me just show you visually. So let's say this is a component and there was a node u, and this is one more component, and this is a larger component, let's say, and there was a node v. Now I was finding the, I wanted to do the union of these two cells. So what happened, so I just found the parent of this component, so it came out to be pu, and the parent of this component came out to be pv. Okay, so now I can see pu size is basically less than pv, this component size. So what I'm saying, this component, I will call this component, I'll say, hey, now you are not the parent. I'm saying the parent of this is now pv, and you will be merged to this component. Okay, so basically the size of this component will be increased by whatever is the size of the component pu. So size of this component pv will be increased, and this is the size of pu. Okay, so the size of this component will get increased because this many nodes will be included in this component, right? And there can be vice versa case. Then it's possible that this is pv, the smaller component, so you will be adding the uh, and this might be pu, so pv might be added over here, right? So that's what I am doing in the union. So this is if and else, which I have written over here, that does the same thing which I have told you. So I hope you got an idea about the disjoint set that I'll be using. Now let's go back to the maximum connection. Okay, first of all, find out all the components, and then one by one select the cell with value 0 and convert it into 1. Let's start the implementation in finding out all these cells that are having values 1, or let's say connected components having value 1. So first of all, I'll find out n equals to, I'll find out the dimension of the grid. Then I have created a disjoint set. I have passed the dimension n, so it will basically create n cross n parent array and n cross n size array that we saw right now, right? So here we saw it. So this will be called, and this initialization will take place. Now let's go back here. Now we are finding and connecting the components having value 1. So we are using disjoint set to store to denote a component, disjoint set to denote a component, and we are also maintaining the size of every component that we saw inside DSU, right? Now I'm iterating over entire cell, row and column. And if I find a cell with value 0, I'll just continue because in the part 1 I'm not needing this cell, right? I only need the cell with value 1. So now let's say if I find a cell with value 1, I will be looking at the adjacents of it. Okay, so directions I have given -1, uh, up, down, left and right. Okay, so you can find out this. Basically I'll be just modifying the indexes in this manner. Okay, so I'll be finding out the adjacent new row and new column, and it should be valid. Is valid basically checks if the cell is inside the matrix or not. Okay, so row number should be greater than 0, column number should be greater than 0, and r and n should be less than n. Okay, then coming back, so new row new column is valid will say is it a valid cell or not, and its value should be 1, the addition should be 1, then and only then they can be combined. So I'll combine them, and this node, see what I have done. Let me explain what these formulas are. So what I have done, we know that 0 comma 0, let's take a cell having n equals to 3. So I'm writing down the dimensions of every cell. So that would be 0 comma 1, and this will be 0 comma 2. So now here will be 1 comma 0, 1 comma 1 and 1 comma 2. So now this will be 2 comma 0, 2 comma 1, and this will be 2 comma 2. Now we know that inside the DSU we have created a parent array, and the numberings are linear: 1, 2, 3, 4, 5, 6, 7, 8, right? So this is the parent array. Let's say this is the parent array for the current grid, right? So now what I want to link this cell this one with index number 0. I want to link this cell with index number 1. I want to link this cell with index number 2, this with index number 3. So what I have done, basically I have taken this formula. So node number will be found by what? Take the row number, multiplying with n, and add the column value. So let's see. So if I take the first one, this one, row is what? 0. What is n? 3 plus column is what? So I get node value equals to 0, this one. Now let's take one more, another cell. Let's take this one, 1 comma 0. Row is what? 1. N is what? 3 plus column is what? 0. So I'll be getting 3. So this cell, you can see it is mapped with the node value 3. So that's what I have used, and this will be highly used inside the function. Here also you can see for the new row into n plus new column for the adjacent cell. I have used the same formula. Okay, I hope you got an idea about this formula. Now I am just checking if I find an adjacent one, adjacent node that is also 1. So I'll combine them. So this last step, that is 57th line, what I'm doing, let's say I found a cell that was having value 1. Then I checked the adjacent one and I found that this adjacent one is also 1. So what I did, I basically combine them and put them in a same component. So I'm just doing the union of these two nodes. Okay, so I've just done the union, and this is what we do to find all the components. Okay, so now after finding all the components, now here comes the answer calculation. To store the answer, I have used an answer variable. Okay, so we are going to find out all these cells having value 0. So row, I'll start the iteration. Now I will ignore the cells with value 1. Now whenever I see a cell with value 0, I will find out the adjacent components. What is this set used? I will just explain in a few minutes. But focus, now I'm finding out all the adjacent cells, adjacent components. Okay, so I found their row number and column number. Okay, I find if the cell is valid and if the cell value is 1. Okay, so I found the adjacent node number, right? Whichever cell is adjacent to me. Let's say I found I comma j that is equivalent to 0, and then what I got to know, I found that this neighbor is having value 1. So I want to find out this cell is part of which component and what is its size and its size. Okay, so that's what I'm doing over here. So I got to know the node number, then I go to the disjoint set and I'm finding the parent of it. Now I got to know the parent of this component. Who is your parent? I asked this, who is your parent? Okay, after getting the idea about the parent, I got to know from disjoint set. Okay, the find function will be used over here using path compression, and this will be returning me the component parent. Okay, and let's say this is saying that my component is node, let's say node number 3. It is saying my parent is node number 3. Okay, then what happens? There is one more adjacent cell. I ask the same question, like you are part of which component and what is your size? So basically I'm finding its parent, and this also says basically I'm part of node number 3. I'm basically inside the component whose root is node number 3. So here you can see this and this are part of the same component, right? So I don't need to include the size contributed by this, because I just need to select only one size because they are already part of the same component. Let's say it says this cell says my component size is equivalent to 7. This cell says my component size is equivalent to 7. But actually they are part of the same component, right? So you need to include this 7 only once. So you are finding out unique components that are adjacent to this cell 0. So I'll use a hash set over here, a set data structure, in order to store the unique component parent. So I'll say node 3 is a unique component. Then again, if I get node 3, it will not be inserted. If I get another component, let's say node 4, then it will be stored. Okay, then I just need to do this sum of the size of this component, and that will be my temporary answer. Okay, so after finding out all the unique components, I am just taking the initial size as 1 because the cell 0 will be converted into 1, and it will also be contributing to the overall size. Okay, here size sum equals to 1 because cell row comma column equals to 0 will get converted into 1, and it adds up to the size of the component. Okay, so that's why I have taken this initialization with 1. Then I am finding out the what were the unique components adjacent to cell 0, and I'm just adding up their size by just looking inside the disjoint set and going and finding their size of that component, and then I'm comparing with the answer and updating the answer with maximum value. Okay, so this is the part 2. Okay, and now there's one more edge case. Let's say if you are given a grid with all values 1, so you will not find out any cell with value 0. So this for loop will not be iterated and your answer will remain what? 0. But actually what should be your answer? Your answer should be the entire grid component that is having all values 1, right? Let's say if I give you a matrix having all the values 1. So here you will not be finding out any cell having 0, and you will not be able to convert it into 1. So what we have used initialization for answer with what? With 0. So now if we directly return the answer, then for this kind of corner test case, your answer will be wrong. So what should we do? We should find out that what is the maximum component size inside this grid. So for that, I have used the last step. That is, if all the cells are 0, then you won't find any cell having value 0. So in that case, find the size of the largest component. So I'm iterating over all the nodes, that is n cross n nodes, and I'm just finding out the size of all the nodes, the maximum one. So this is how I'll be handling the corner test case, and then at the end just return the answer. Okay, quite a lengthy code, 150 160 lines of code. Okay, so yeah, now let's try to compile it, and let's try to see the compilation status. So it is working perfectly fine, and let's try to submit it, and we can see that the problem has been successfully submitted. So this was quite an interesting problem, and I would like to recommend everyone that at least try to solve this question from scratch. Okay, after watching this editorial as well, try to implement this on your own. You will find it very much interesting to do the implementation. Okay, so that was it for in this video. I hope you really enjoyed the solution, and do hit the like button and share down your approaches in the comment section below. So that was it for today. I will be seeing you in the next video. Till then, keep coding.